Okay, let's go ahead and get started with lecture 10. And I want to try to pick off from where we were last time. We were talking about an actual practical problem and sort of how to think about it in terms of using our theory in several, I guess, more practical ways to think about it. So to catch up where we were talking about unaliased bandwidth and how to control it and what do we mean by unaliased bandwidth. And from last time, unaliased bandwidth simply meant the bandwidth is, or the aliasing is controlled. There's a certain amount of attenuation on alias signals in the bandwidth of interest. So we're beyond the, I guess we'd say the ideal low-pass filters or ideal anti-aliasing, and now we're seeing how the filter we're using is impacting our sampling mechanisms. So let's go back to our example where I'll just try to sketch it so we don't have to cover everything in gory detail. But we had an anti-aliasing filter we were looking at. And I think I was calling this frequency omega 1 and this one omega 2. And we were saying that omega 1 was what? 2 pi 1000 for this case. And omega 2 was 2 pi times 3000. I'm writing it that way so we can just, at a glance, go back and forth between hertz and radians per second. So 3000 hertz, 1000 hertz. And we had, what, a pass band. This was the pass band. Nothing's attenuated here, so kind of an arrow saying that's 0 dB of attenuation. Nothing's being attenuated. And down here we're saying this is minus 30 dB of attenuation. So the power is being attenuated by minus 30, or like a factor of 1,000. So that's where we started. And I think I was trying to say that suppose, one way to think about this anti-aliasing filter situation is to imagine that this kind of guards the input to our system. This protects us. Well, suppose you had a extremely broadband signal. In some ways, receiver noise is such a broadband signal. So we're going to suppose we have an XC j omega. And this is just kind of for the purposes of thinking about what's happening. Because really, you don't usually have total control over what appears at the input to your A to D. If you did, you wouldn't need an anti-aliasing filter. So worst case, a super broadband noise signal. So if that's at the input and it goes through our anti-aliasing filter, we sketched last time, okay, this signal, after going to the anti-aliasing filter, and let's go ahead and convert into frequency. So now we're going to talk about frequency in hertz. Also, it saves me from having to write 2 pi all the time. So now we're going to end up with something like this, and now we're in F in hertz, which is many times how things are going to be specified or talked about, so I'm going to put this in hertz. So if we peel off the 2 pi's, 1000, I think 3000, minus 3000. And that's simply because what? X of j omega times, we just simply filter the continuous time signal, which is broadband, with our anti-aliasing filter here. What does it do? It just paints out the anti-aliasing filter. So now the fun begins. What happens when we sample this broadband signal after it's gone through the anti-aliasing filter? And that's where we're going to have to say, nope, the anti-aliasing filter isn't good enough, or we're going to have to say we're going to have to live with the bandwidth that's unaliased, or we're going to have to say the sample rate must be at least something. So that's where we're headed with this analysis. So if we go back to our kind of original theory, I'm going to call this S for sampling and AA for anti-aliased. And this is a sketch. Notice I'm calling it kind of a sketch because I'm not keeping track of the amplitudes because it's mostly notional at this point. So what happens when we sample? Remember from the theory that means we end up with all these shifted copies of things. So now, ... we end up with shifted copies. And
how did you shift it?
Because we sampled it.
Oh.
So it's back to step one. We're sampling things. We've got these shifted values. And where are the shifts? They're at fsamp, whatever that is. Our task is going to figure out what does fsamp need to be to protect the bandwidth of interest. That's really what it comes down to for this type of problem. And I think for the problem that we were working, we were saying, okay, if this is f1, which is 1,000 hertz, the question we were asking ourselves is, what value of fsamp results in alias signals with having, I guess, we'll see, greater than or equal to 30 dB of attenuation. So what value do we need so that the alias signals will be at 30 dB or more of attenuation? And that's kind of why we started drawing this thing way back at the beginning. You have to draw a line somewhere. And I drew it at minus 30 dB. And just as a refresher, why did I choose 30 dB? Well, it's a good value that practically works in many applications, but your application will steer you to the right number. Maybe you can get away with minus 20. And as we go through this, you'll see that makes your life easier. Maybe it's minus 60 for your application. That's going to make your life a lot harder. But either way, you have to draw a line somewhere, because we're going to say anything below this we don't care about. So let's move to our next step. Okay. So that's the problem we're trying to solve. I think what we wanted to do next is try to catch up and say, okay, just to kind of give you a feel for what's going on, let's choose a value of fsamp and see where the shifted copies end up and where the aliases are. And I think right at the end where we quit, I said, let's redraw the picture, and now let's be a little more serious about where the signals lie. And just let fsamp equal 4,000 hertz. And if you like to think about omega s, that'd be just 2 pi times 4,000. Same thing. So now we're going to redraw it. Sampled version, anti-aliased. Broadband signal went through. Now let's see where these shifted copies land. And now I have to be more careful. I want to try to make this a reasonably well-scaled sketch here. And we're going to do it in F, in hertz. So the pass band is out to 1,000. And the stop band, 2,000, 3,000. Stop drawing there. Now we're sampling at 4,000 hertz.
Does the pass band mirror to the negative values as well?
Yeah. This is a standard low-pass filter with real coefficients. And so let's annotate it as such. So now the shifted copies come into play? Well, we're sampling at fsamp is 4,000 hertz, so let's redraw the signal. What the passband is 1,000 hertz, and then what it takes 2 to go down there, 1 here. Draw the same thing on this side. Dot, dot, dot. Now when we look at this, what do we see? We see that the shifted copies are aliasing, and we talked about that before in other lectures, where when these signals are on top of each other, you have aliasing and you can't recover the signal. But we notice that if we kept drawing this on down, right? We just stopped at minus 30 because we had to stop somewhere. But you can keep drawing these on down, minus 40, 50, 60. But we're saying once you get past minus 30, I don't care. The bandwidth is good enough. It is clean enough and it is recoverable enough. So by looking at this, hopefully you can see that, hey, this is pretty nice. The bandwidth between plus 1,000 hertz and minus 1,000 hertz looks good. And why does it look good? Well, first of all, the alias copies that are continuously there's aliasing, but those aliases are attenuated by 30 dB or more. They're attenuated by 30 dB here, and they continue to get more and more attenuation as they alias closer and closer to DC. So that's good. But there's another thing that's good too, right? Look at the passband of this filter. There's 0 attenuation in the passband. So the good news is, if fsamp equals 4,000 hertz, I guess you can say requirement is met. And that requirement is that the alias samples have to be attenuated by 30 dB or more. Now what we're going to see is, suppose fsamp was not 4,000 hertz. If fsamp is, I'm just going to pretend I can pick this up, this shifted copy, and move it freely. I need to bring some paper dolls so I can just shift these around. But if I made it 3,000 hertz, then this would start to come in here and encroach on this passband. And if it does that, then we will not meet the requirement over plus and minus 1,000 hertz. So if fsamp is 4,000, requirement is met for f in that region, and so we'd say sometimes the word usable bandwidth, maybe I misspelled usable, bandwidth is plus and minus 1,000 hertz. Sometimes you might just say it's 2 kilohertz because you have a total of 2 kilohertz of bandwidth, but you can see that's definitely usable, not attenuated by the passband, and the aliases are controlled. So that's what we're shooting for here. So let's see if we can summarize this. So if fsamp is greater than or equal to 4,000 hertz, then unaliased bandwidth, and unaliased just means it's controlled to 30 dB or greater, is what is greater than plus or minus 1,000 hertz. And then there's a side bullet here that says the passband of the filter starts to limit the bandwidth. Remember, that was from up here. If we pick up this copy and shift it out, let's say we sample at 5,000 or 6,000 hertz way out here, then what's going to happen? Well, that means we're unaliased down to here, but the passband of the filter is rolling off that data, so can we really use it? I mean, maybe, maybe not. It's definitely not matched to our situation. And of course, our second example is if fsamp is less than 4,000 hertz. Alias limits aliasing limits the usable bandwidth. And another thing that we have to keep in mind is, why did we have to sample so fast? Well, the skirts of this filter had the slope that it had. If you can imagine, suppose this was an ideal filter, then how fast could you sample? You could sample a lot less because it's perfect, right? You could move it over and sample at 2,000 hertz, and you'd be fine because it's a perfect filter. The slope is infinite. But we're talking about practical filters, so we can't do that. So there's going to be a trade. As an engineer, you have to trade, well, what's the complexity of the filter? What's the order of the filter that I want to put in? You know, the cost of all those parts to give me the really steep slope. So slope of the filter skirts are a factor. So that's part of your trade when you're trying to figure out what do you really want to do.
I have a question.
Yes.
In this example, does omega S plays a role in something?
No, I just left it there just because of your question at the beginning of sometimes it was confusing about, am I using hertz or am I using radians per second? And many times things are specified in hertz, but all the analysis in our textbook uses radians per second. And so now we're kind of starting to move past the theory and into practice, so we've got to get our arms around both. So I'm going to be kind of going back and forth between them. And if you're confused, definitely ask a question. I just want you to be able to apply this theory to, you know, a problem given in hertz. That's typically how it's done.
How did you calculate the 4,000 hertz sampling? Because I know why you needed it for no aliasing between 0 to 30 dB. But how did you actually get that?
Well, in my mind, I just sort of shifted it out.
Oh.
But we're going to talk about it sort of a less clunky way next, which I think will help you be able to see it a little easier. And that brings up a good point is, why did I talk about it this way? I think there's a slightly easier way to think about it, but this ties back to all the previous theory. So now we're standing on 3 lectures of theory of delta functions and sampling and everything else that brought us to this point. Now we're going to start talking a little bit more heuristically on like tools and methods that lean on this, but are not exactly the same. Or they turn out to be exactly the same, but they're easier to deal with. So with that in mind, let's talk about a concept called the folding frequency. So if any of you heard of that in regards to this folding frequency? Folding frequency. This is a useful concept for analyzing aliasing. And that's the way when I'm in my everyday work, we're going to go through kind of how I think about the problem using this concept of folding frequency. Because I think that's a little bit more common for everyday engineering practice, at least it's been my experience. So we're talking about this because it's a useful concept for analyzing aliasing. In fact, I think in most of my day-to-day work that I deal with this type of stuff, I usually think of it in terms of this folding frequency that we're going to think of. And that with the shifted copies of the spectrum, I think about sampling in that context in that way only when I'm thinking about bandpass sampling, which we'll talk a little bit about later. But in my mind, when I think about sampling, I have two ways of thinking about it. And I use those 2 ways depending on the problem at hand. Of course, it's all the same math, but it makes it easier when you, at least to me personally, when I'm thinking about one problem to use it one way and another problem to use it another way. So with that introduction, let's get started. So we already know from all the theory we've been talking about that given some sampling rate, it has to be greater than or equal to twice the Nyquist frequency. Right, and remember the Nyquist frequency was the highest frequency that was present in the spectrum. And I think some of the other concepts we had was what? Omega S, we can also write as 2 pi over t, where t is the sample period. And given our very handy frequency scaling identity here. And that's from going continuous time to discrete time frequency. That means in some sense omega s equals 2 pi. And that's pretty nice because we all know that discrete time Fourier transforms or discrete time spectrums always are periodic with 2 pi. That's written in stone, and here we go. We sample it, we get to this, and well, by golly, things are going to be periodic with 2 pi, and isn't that great? Because shifted copies at 2 pi are what we end up with, right? Because we're shifting things. So with this in mind, hopefully we'll move forward and say, well, that discrete time spectrum repeats every 2 pi. So what's the unique part of that? Well, you have to select some portion of that. So you can go 0 to 2 pi is the part we want to look at, or you can go minus pi to pi. And I'm going to look at it from this perspective of the unique frequencies that I'm looking at are between minus pi and pi. So omega is less than plus pi and greater than negative pi. It's in that region. And as it turns out, everything that's outside that region has to alias in. So the entire universe of frequencies, once they're sampled, have to alias back into this world, because that's the unique part. Everything else is just a copy. It's periodic with 2 pi. That's sort of the law. So let's play around with this and see what the obvious implication is. So if we divide both sides by cap t, or the sample period, what do we get? I get that expression. And so, but what is pi over t? Remember that omega s was 2 pi over t. So that would tell me that omega s over 2 is pi over t. So that means I can bring that down and say, let's go omega s over 2, and that's just omega, and that's minus omega s over 2. But most of the times our problems are not in radians per second, they're in hertz. So let's divide everything by 2 pi and get back to hertz. So if we do that, we're going to get f samp in hertz over 2. Divide this out, that's just some frequency f minus f samp over 2. So all the frequencies that are coming into our system are going to be aliased between minus f samp and plus f samp. And how did we get there? We got there because we know that all the frequencies have to be here, and just by scaling arguments, it's going to have to end up here. So as frequencies, wherever they are, they're going to end up, once we're sampled, between these two, minus f samp over 2 and plus f samp over 2. Now the reason this is useful is because the folding frequency is this f samp over 2. So the question we're going to ask is where do frequencies, so where are the frequencies such that f, which is some frequency, is greater than fs over 2. So where do frequencies alias? Where are they going to end up? We know they end up in here, but the question we're going to ask is where, because that's what matters. So how do you do that? And that goes back to this concept of the folding frequency and the fact that things are periodic with 2 pi, and we've scaled it down to this f-samp. So here's the rule that we're going to use to make this pretty easy. If we have a frequency, so this is for any frequency, f, such that f is greater than f-samp over 2, what are we going to do? We're just going to add or subtract. We're simply going to add or subtract multiples of f-samp. And I think we can write that out, multiples. And we use the same f-samp. Kind of writing it out in words, and then we'll put some math on it until the result, we'll call it f prime, satisfies f prime must be less than f-samp over 2. And these multiples could be 1, 2, 3, 4, whatever. And this is kind of equivalent to adding and subtracting and shifting it by the sampling frequency or by 2 pi in the discrete time domain. And the reason we call this the folding frequency is because everything that's greater than this folds and goes back into that bandwidth of plus and minus f-samp. And we're going to go through an example so you can kind of see how to draw it and what makes it called the folding frequency. So we're going to go back and look at our previous example and then just apply these sort of heuristic rules to it. So let's go back. And this is the previous example. So there's our filter, and this is in hertz. And now we're going to apply that concept of the folding frequency and kind of look how things happen. Well, if f-samp equals 4,000 hertz, then f-samp over 2 is 2,000. And so we're just going to assume right off the bat, let's pretend we're going to look at what's the implication of f-samp equal 4,000. Well, f-samp over 2 is 2,000, and that's what is called the folding frequency. And so the utility of this concept is that means I'm going to just draw kind of a red line on here at 2,000. And everything outside this line has to alias back in somewhere between plus and minus 2,000. All the frequencies out here have to come back in there. So in some sense they fold over, they're out of there, and they fold back in somewhere on this side. So now let's think about this and apply our rule, starting with, well, if that's the case, what about all this bandwidth over here? And so I'm just going to put some hash marks on it like that. What about all this bandwidth over here? It is certainly greater. If we go back to our rule, these f's, these frequencies are greater than f-samp over 2. So I'm going to add or subtract multiples of f-samp until it satisfies a frequency less than that. So it's kind of wrapping back in. Sometimes people use the word wrapping. So if these frequencies are greater than f-samp, then we're certainly not going to add multiples of fsamp, right? Or they're greater than fsamp over 2. So if I just grab a point, 2500, and add 4000, I'm even farther out. So what I want to do is take this frequency, like 2500 for instance, and subtract 4000. If I do that, where does it end up? Well, 1000, 2000, 3000, 4000, minus 1500, right? So it's over there. What about the top part here? Right past 2000. Well, if I subtract fsamp of 4000, I end up at minus 2000. And of course, you can see where this is going. If I take 3000 and subtract 4000, I'm at minus 1000. So all that bandwidth aliases in right there. In some sense, it folded over and ended up on that side. Of course, we can do the same thing with this bandwidth, which I'll just put some dots on it. So everything over here, we can apply the same logic. Is it greater than fsamp over 2, the folding frequency? Yes. Minus 3000, subtract 4000, I'm over here, so that's no good. Add 4000, I'm over here at 1. And of course 2000 is the same. So we end up with that dotted bandwidth aliasing in there. And that's important because after you've sampled this plus and minus fsamp over 2 is your digital universe, right? That's your discrete time. Everything that was presented to your A to D now lives in minus fsamp over 2 to plus fsamp over 2, which is minus pi to plus pi. That's everything is now aliased into there. So what we're showing is if we controlled things to minus 30 dB here, we can easily see where it lies here. Or if someone said there's a big giant frequency spike at 4000, where does that end up for some reason? Well, if you subtracted 4000 hertz from that, that would put it right there. So the concept is kind of useful for finding where things are going to end up in frequency after sampling and kind of staying in the hertz domain. Sometimes that's useful. I find it useful for troubleshooting things or trying to figure out if I have a discrete frequency, where is it going to end up in my sampling. So if we look at it that way, you can see that the usable bandwidth is again this plus and minus 1000 hertz. I hope that's clear. And I also wanted to go back and show you from our previous drawings that this may seem like it's maybe a little heuristic, or maybe you've seen it before so it's old hat, or maybe it seems totally different than what we just spent time on. Well, if we go back to our original stuff based on all that theory, and we just look at what's going on at 2000, we notice all these shifted copies. Well, what's kind of interesting, if I shade this stuff in red over here, well, that little red wedge is the same red wedge over here, and it's the same one over here. Because remember, all these are shifted copies, right? It's just the same thing picked up and moved. So, but wait a second, that's just what we drew on the other page using the heuristic of subtracting sampling. So instead of using that theory and drawing all this out, you can just skip and do this if it's easier. It's like whatever you need to solve the problem. And I typically do it this way when I'm solving problems involving anti-aliasing filters. And we'll talk about other ways to I think about the sampling in this manner with the shifted copies when I'm doing the thing called base, I guess, when we're doing the, what is it, the bandpass sampling, which we'll talk about later. So now let's use our little trick here to analyze two other cases very quickly using this technique. So what is usable bandwidth if fsamp is 3000 hertz? So now we've reduced it. And so boss might say, hey, let's reduce it to 3,000 hertz because that saves a lot of data that we don't have to pass through the system. Or some other interested party wants to reduce the data rate. And that's going to be more than good enough for our purpose here. So there's our handy filter. But now, if fsamp is 3,000, then fsamp over 2 is 1,500 hertz. So if we go back and draw our folding frequencies, we'll notice pretty quickly this is 1,500 hertz. What happens to 1,500 hertz if we sample at 3,000? Well, minus 15 minus 3,000 is minus 1,500. So this kind of alias is over there. They're in both places at the same time, sort of. What about 2,000 hertz? We subtract 3,000, that's minus 1,000. So that point goes over here. What about 3,000 hertz? We subtract 3,000, that's at DC, 0 hertz. So all this aliased to that location. Similarly, we can go look at minus 2,000 hertz over here. Add 3,000, what do we get? That'll be 1,000, right? So this aliases to there. Minus 3,000 aliases to there. And sadly, all this green bandwidth is aliasing into there. So that's not particularly good because that looks like there's nothing available now. All this bandwidth will be aliased. Or you could look at it, it's not controlled to the spec. So the answer is none with requirement whoops, can I spell requirement of attenuation greater than 30 dB. Now you can see, what if we redrew this thing? Instead of 30 dB, what if you said, well, really you only need 20 dB or something like that? Well, that meant this whole thing would be shifted down, right? And so maybe that's the 20 dB line. I don't know, it might be. In which case, then all this would be usable. But hopefully that kind of shows you the trade. You have to start over and say, well, I can't control it to 30 dB, so I got to go back to the requirement. I mean, maybe this requirement was made by somebody who didn't understand what it needed to be. But now you can kind of see the trades, because you're going to have to sample faster than 3,000 hertz if you need 30 dB. It's just with this filter. Or you can go back to whoever's designing the filter and say, nope, we've got to start over with that design. So that's part of the trades. So now, I think we've got all that on one page. Let's go to a slightly more benign case and say, well, what is usable bandwidth if fsamp equals 6,000 hertz? So we've got a 6 kilohertz A to D running here. What's going on now? So let's draw it. And this is, we'll call this F. We'll make our lives easy. We're going to change it. Instead of hertz, we'll use kilohertz. thousands of hertz. So now I can just put 1, 2, 3, 4, 5, 6, -1, -2, -3, -4, -5. So this is in kilohertz, so this is 1,000, 2,000, 3,000, 4,000 in hertz. So we're changing it a little bit just to make it fit easier. So if that is the case, what's fsamp over 2? 3,000. So we'll go back to our colorful pens and say there's my fsamp. Well, how about that? There's really nothing. Everything outside this is less than 30 dB. So that's good news. So what's the answer then? Well, you could say the entire bandwidth is controlled, but is it really usable? Well, look at this passband here. This is the part where we're at 0 dB attenuation. This is the part where we're at -30. So really, it didn't buy you very much, right? 6,000 hertz, you're still only at plus and minus 1 kilohertz. And it's kind of, we'll make it an either or, is plus and minus 1 kilohertz or plus and minus 3 kilohertz if the passband doesn't matter. So if you don't care about the fact that this signal here at 2 kilohertz could be highly attenuated, then yep, you got plus and minus 3 kilohertz, great. If you do care, well, you're at plus and minus 1 kilohertz. I hope that's kind of clear, because nothing here is attenuated, so you can use that whole bandwidth. And so in some sense you could say, well, I didn't really get anything sampling faster than 4 kilohertz. Everything else was kind of not particularly useful. So it really depends on your application, and I hope that kind of going through these examples and talking about the trades kind of gives you a feel. Or you could look at it and say, well, let's extend this on down, right? Maybe you could go back and say, well, instead of 30 dB, what can I buy you? You know, I can get 50 dB of attenuation for alias controlled in this region. So there's a lot of different ways you can kind of approach the problem and think about it, and I hope this helps I hope this tool allows you to make those trades a little easier. All right, so I think that brings us to our next topic. So our next topic is going to get our toe in the water on multi-rate signal processing. And we're going to start that multi-rate signal processing by talking about changing the sampling rates, downsampling, then upsampling, and then finally polyphase filtering and other stuff. So let's talk about it in general. So changing sampling rates. One naive and perfectly good way, at least to start, to think about this is to say, well, I have this data in discrete time, and I don't like the way it's sampled. I want a different rate. Well, we have talked about ways to reconstruct this data. So we can put it through a discrete time to continuous time converter, which basically means a digital to analog converter with a filter on it. And if you remember, what was it? As a gain of t and a minus pi over t to plus pi over t passband, right? And once you get that signal out, you could go ahead and I guess resample it. I think we call that T1. And we're kind of breaking it out into 2 steps, but that's not typically necessary. So we could resample it even in continuous time, or we can make this one kind of D to A converter, and then we'll end up with what we'll call X prime of n. And it's basically the resampled version of this, resampled with the new period, T1. Now, why don't people do this in practice? Well, it turns out going to a digital to analog converter and filtering and then going back through an analog to digital converter causes loss and distortion in signals. And typically, if you believe in the Shannon-Nyquist sampling theorem, which you have to do for this class, then you don't need to reconstruct it because all the information of the signal is contained in the samples. If the signal was band limited and the Nyquist criteria are met. So if we believe that, which we have to, then we don't need to bother with digital to analog conversion and followed by A to D again. So typically this is just not practical. And it's due to losses and distortion by these non-ideal components. A to D, D to A, and of course just the component cost of having to put all this stuff together. So if you could just stay in the discrete time domain and do this, it would be very useful. And so as I said, it can be done, and so we're going to talk about how to do it. We don't need to do that approach. So the first thing we'll do is talk about just rate reduction. And we'll do it by an integer factor. And this, of course, is quite useful practically because many times once you sample something and filter it, you want to get the data rate down. Because more data rate usually means higher cost, more heat, more components. And so you usually kind of want to get the data rate that's just right for the bandwidth of the signal you're trying to process, not anymore. So let's look at sort of a block diagram of the system. And some of our nomenclature here, XD, the D for downsample. And really that equals X, our original sample. But now we're taking every nth sample. So this one is sampled with period t, or sampled at rate 1 over t, or every t seconds. And this one is sampled at some integer factor times t. And typically this whole process is just referred to as downsampling, which typically we just refer to that process as including any required filtering, which we'll talk about. That's our next topic. Why do we need to do filtering? Well, to even decide if this is a good idea and to decide what sort of filtering we would need, we need to look at the relationship between this in the frequency domain to see, well, what is going on? Are these things falling into each other? So that's our next step. How are these related? So the nomenclature for this is, I guess, our goal for this quick derivation. Excuse me. Is basically relate xe j omega, which is our input signal to this downsampling process, to x downsampled e j omega. So what is their relationship? Maybe the easiest way to get started is to recall where we came from. And so sort of as a prologue to this, remember that when we sampled things and we were staying in continuous time, so just if we sampled these with delta function, some signal, we ended up with the shifted copies. I'm rehashing this because it turns out we need this to show the relationship. So this is their basic continuous time spectrum, the shifted copies scaled by 1 over t, and that's the sampled spectrum. Now if you recall from before, we could relate this to x ej omega. And we used, xs of j omega when we scaled it by small omega over t was x ej omega. And that was one of our results prior to this. So when we use these two together, here's kind of our starting point. Let's substitute everywhere we see omega, this small omega over cap t. So now we have an expression for x ej omega that really looks like this. And that's how we're going to start off. So we've got our expression for x ej omega, and we're going to use that version. So we'll go back to this, and wherever we see capital omega, we're going to replace it with small omega over t. And that's k, and omega s is 2 pi over t. So we've got everything in terms of t. So that's our beginning point. So let's take a look at, if we resample this at every nth sample, what would that look like? Well, we know that x downsampled of n is just x of n times m, right? Well, the continuous time version of that is n times t downsample. Whoops, we're in continuous time, so we'll use parentheses. Which, all this looks good so far, and we can write this as, well, what's the period of the downsampling? Cap m times cap t, right? Because we want to take every mth sample. So this sample time, or the sample period, is much larger now by a factor of m. So using that information, we can just kind of jump right to the end and say, well, I'm just going to rewrite equation 1 as equation 2, but instead of everywhere I see a t, I'm just going to put mt. So we end up with an expression like this. Omega, we got cap mt minus k over 2 pi, and now we've got mt again. Now I think what I wanted to do is not use k as a index. Sorry about that. I want to use r as an index, and you'll see why here in a second. R is our index. And mainly because there's a very clever trick here to sort of expand this expression that goes from negative infinity to infinity. So if you didn't think this summation was scary enough, we're going to make it a double summation. So we're going to let r, which was our index here, equal I plus km. So we're going to break it into two pieces. And I'll try to motivate this. So let's see, r equals I plus km, and what's I and k? So k, and let's do it like this, minus infinity, k plus infinity, and I goes from 0 to m minus 1. And so one way to think about this is to think, okay, we took these shifted copies of the continuous spectrum and we're shifting them an infinity number of times, where r is this 2 pi over mt. So we've got all these infinite copies shifted everywhere. Well, what we're going to do is break it into, you can almost think of it as the principal, m components, or m pieces, that's where I goes from 0 to m minus 1. So we'll just break it into m spectrums, and then each of those m spectrums will have an infinite number of copies. And to me, it almost makes it seem like you've decided to take each one of those m sub pieces of the spectrum and copy it an infinite number of times. So you've taken sort of maybe, and I like to think of it in terms of kind of like that folding frequency. We have frequencies between minus pi and pi, and we're going to take a piece of that somewhere in the minus pi and pi and shift it an infinite number of times. And that's where this k index comes from. But we're dividing sort of the principal area into m. That's sort of the, I guess that's my mental model when I think about this, because it's a little bit, like, I don't know how people originally came up with this. It probably took a lot of coffee and a lot of time to break up, because usually you don't think of trying to expand an already an infinite summation. So it's a pretty clever trick. So let's go ahead and try to write this with the substitution r equals I plus km to get started. And then we'll see we'll do some grouping, and then you'll see how this is related. So let's carefully do I equals 0 to m minus 1. It's our first summation. I'm going to put a curly brace here, and I think I wanted to keep this t inside here, which you'll see why later. And of course, k is negative infinity to infinity. It's doing most of the work here. And we've got xc, and we've got what? J, and I want to make this omega over cap m cap t. And now we've got I plus km times 2 pi all over mt. And there's some more braces back there. But really, this is just a repeat of everything we have here, except now r is I plus km. We just substituted it in and moved on. Now the next part of this trick is to accumulate certain terms together. So we're going to group omega minus 2 pi I terms. And we can do that because notice the omega term is under cap mt, and so is this I times 2 pi is also over mt. So if we do that, I'm going to put an equal sign here and give myself more space. Hopefully you can see what's going to happen after this step. M minus 1 over t and now we've got xc of j. We have omega minus 2 pi I over mt. And what does that leave us? Well, it leaves us with the 2 pi times km over mt. Well, if the m's cancel, it just leaves us 2 pi k over t. So now we're back to this. So let's see if we've got that. And this is, let's see, this is equation 4. Our next step is to realize, even though equation 4 looks very messy, I'm going to go back to equation 1 and compare them. And the insight here is that if we look, okay, 1 over t, the summation of k to infinity, we've got that, check, xc, j. This is omega over t, this is omega minus 2 pi I over mt, and this is 2 pi k over t. So the insight is if omega was equal to a shifted scaled version like this, of equation 1, we could substitute equation 1 into equation 4 and make it a scaled version of that. So that's kind of the tricky last step of saying xd of ej omega. This is where I'm going to say sub 1 into 4. So equation 1 into equation 4. Leaving us with our final expression, which is x of e to the j, and now it's a shifted version, omega minus 2 pi I over m. And that is the relationship that we were out to get. So what is the relationship between the downsampled spectrum and the original input spectrum before the downsampling? So let's try to unpack this a bit and summarize. So the downsampled spectrum that's this xd e to the j omega is m copies of the original spectrum which is x ej omega scaled in magnitude and frequency. And the scaling comes from, well, it's scaling and shifting, but the scaling comes from this divide by m in the frequency variable, and the magnitude comes by this 1 over m in the expression. So let's do a kind of a simple example to kind of get a feel how this works, where m is going to be 2. So let's do an example. M equals 2, and our Nyquist frequency will be our sampling rate over 4. And we do that kind of to make our life easier in seeing what's going on. Probably right off the bat, we wouldn't want to have an alias signal to look at and then start trying to figure out what this means with a whole bunch of alias signals running around, right? That would be that would make our lives harder. So to start off with, I think we'll use a different page so we can kind of put everything on the same plot. So let's look at our continuous time. As specified here, we're saying, okay, we've got a band-limited signal, Nyquist frequency. We go back to our expression for what does the sampled version of this signal look like. And we've been here before. Let's see if that's omega n. We get a whole bunch of shifted copies. That's scaled, right? And that's omega n, 2 omega n, 3, 4, 5. But omega s, as we said, is 4 omega n. So 1, 2, 3, 4. And we draw another copy. Dot, dot, dot. One, two, three, 4. Dot, dot, dot. So we've got our scaled version of what things look like in frequency. And we're kind of going through it step by step, just as a reminder. And now, the fun part, right? We're going to go from continuous time to discrete time by the scaling. So using our favorite scaling routine, what do we have here? omega is that. So if I want to scale this frequency, omega n times t, what is that in discrete frequency? Well, omega n was omega s over 4 times t, right? And omega s is what? 2 pi over t. There's our 1/4, and there's our t. So the t's cancel. 2 pi over 4, that's just pi over 2. So if we scale omega n, it goes to pi over 2. So now we can just, in our mind, say, well, that is going to go over to pi over 2 in my next plot. So pi over 2, pi, 3 pi over 2, 2 pi. Pi, 3 pi over 2, 2 pi. This is omega dot dot dot. And that's not 1, 2, 4. This is what? X of e j omega. All right, now we've got it all aligned. Now we can start the problem, right? Let's go back to our formula here. And let's just write out both terms just so we can kind of unpack this. So this was our amazing formula. So what is it if m equals 2? It's going to equal 1/2 x of e to the j. I equals 0, then that's 2 pi times 0 over m. Well, that's great. That's just going to go away. So I got omega over m, but omega is that, and m is 2. Plus 1/2 x e to the j. I equals 0, then I equals 1. M minus 1 is 1. So that's going to be what? Omega minus 2 pi all over 2. So applying our formula we derived, there it is. Now, what does it look like in the frequency domain? So let's try to, if we can get it, we probably can't get it all on the same page at the same time. So let's just look at it term by term. Let's say 1/2 x of e to the j omega over 2. Just look at that first and work our way through this. So right off the bat, let's go back to this. And notice that when omega, little omega, is pi over 2, what's the value of the spectrum? It's 0. So what value will omega have to be in this argument so that we have e to the j pi over 2 with a value of 0 there? Well, it's going to have to be twice as big, right? Because if I put in pi here, omega equal to pi, then I get x of ej pi over 2. I know what that is because I look down here, x ej pi over 2 is 0. I'm going to put a pi here, and hopefully that makes sense to you. If you put in a pi for omega, it's e to the j pi over 2, which we look up here, x e to the j pi over 2 is 0. So that's kind of a clunky way, maybe too clunky, of looking what happened. And maybe you can just see that because you've scaled functions before. Well, if I'm going to divide the argument by 2, and this is the argument, then everything here is going to have to be doubled in size. Otherwise, I won't get the same result, right? So when we do that, everything here doubles. So that's pi, 2 pi, 3 pi, 4 pi. And now we scale it by 1/2. So now we're at 1 over 2t minus pi minus 2 pi minus 3 pi, etc. Excuse me. And this is this goes out to 4 pi. Right? 2, 3, 4 pi. And why does it go out to 4 pi? How did it get there? Well, we know that there's a copy of x e to j omega at 2 pi. So if I'm going to divide it by 2, I'm going to have to put 4 pi here. 4 pi divided by 2 is 2 pi to get the same thing I got here. So hopefully that's clear how this whole thing is basically expanding by this factor of 2, courtesy of dividing it by 2. So that's 2, 3, let's say that's 4. But that's only half the answer, right? We still have this portion to deal with here, this 1/2 x e j omega, but now we have this offset. So let's look what happens when we apply that. Pi, 2 pi. I think the easiest way to do this is to always have kind of in your back pocket when you're trying to look at these and carefully work through it, is to have this x e j omega in your back pocket. Because then you can always apply the argument, whatever this is, into the formula, and you'd better get something that lies on here. So let's do that. This is what? This is 1/2 x e to the j omega minus 2 pi all over 2. So this one is more complicated. So let's just start plotting it. How could we do that? Well, we could just choose an omega out of hand. Let's just choose one, any one, right? Let's choose omega equals 0. If that's the case, 0 minus 2 pi is minus 2 pi divided by 2 is minus pi. So we have 1/2 x e to the j minus pi. So you could go back up here and look and say, okay, I've got pi minus pi over 2 minus pi. That is 0 at minus pi. Well, how did I get that? I got it by applying omega equals 0. So there's a point. Let's do another one. Omega equals pi. So pi minus 2 pi is negative pi. Divided by 2 is negative pi over 2. Let's go back up here to our handy plot. X e j omega minus pi over 2, that's also 0. Let's do one more, 2 pi. 2 pi minus 2 pi is 0, divided by 2 is still 0. So 0 is, that's that 1 over t, it's the top part. So it's 1 over t, and scaled by 1/2. And if we fill in these, you're going to end up with a spectrum that looks like this. I'm not going to go through all the points, but there are probably multiple ways to think about this. But the easiest bulletproof way is to just plug in vectors of omega to this formula, and you have this lookup table here in some sense. So that's more the brute force mechanical way to not make a mistake. So what happens when we put all this together? Because we have to add these two together, and you can kind of see this example was contrived to completely fill up the bandwidth. Right? So if we add these two functions together, what do we get? The desired spectrum. So let's add them together and put them on the same plot. And so we get x d e to the j omega. And this is where we end up with this sort of triangular looking 1 over 2t spectrum. Dot, dot, dot. And that's a good thing too, right? Because didn't we always claim that anytime you have a discrete time function, it better be periodic with period 2 pi? And this function is, and so this is certainly a DFT, or it's certainly a DTFT. It's a spectrum. So I think we'll stop here, and next time we'll do an example with m equals 3. But more importantly, next time we're going to do a review for the exam, which is I think a week from Wednesday. So next time, exam. Talk about the exam, and we'll stop here.